a great topic, though. Asynchronous programming. It's been around forever. It's not new. It's been around for decades. One of the laws that you hear quoted a lot or talked about is Amdahl's law, for example. That was 1967. This stuff has been around. We probably have been, in our realm, more affected by Moore's law from 65. The doubling of the transistors every 2 years has probably had a bigger impact on our lives until the last few years. So originally, in our platform, we always had one core, one hardware thread. You could do sort of asynchronous programming way back in fairly early Windows, but all you really got was a responsive user interface. You didn't really get any parallel processing. And even when you tried to do multi-threaded programming for a server, if you did it on your desktop, the problem you had was that you were getting concurrent processing but not parallel. So then you would promote this software to a real server that had multiple cores or multiple threads running, hardware threads, and strange things could begin to happen because you didn't see those things on your local machine. You could do things that gave you a responsive UI. You could have, way back in 2000 or earlier, you could have Query Analyzer and you could click the cancel button and it would cancel a query. But nothing was happening in parallel. You had one hardware thread, one core, and that began to change about 2004, I guess, when we had hyper-threading. So all of a sudden, then the ball game started to change. And .NET has always given us ways to do threaded programming, asynchronous programming. It's evolved over the years. But I'm going to be talking tonight about the latest incarnation in the 4.5 framework. So there's some pieces in there that have changed fairly dramatically in making coding a little bit easier. So that's what I'm going to focus on tonight. The things to remember about asynchronous programming, I think, that are most important, one thing is sequence. Things don't happen in any particular sequence anymore. As soon as you go async, then if you're in a loop, the 75th thing can happen before the second thing can happen. If you have partitioning schemes going on in the data, then you get chunks of things that are out of order. You can't rely on sequence anymore at all. And we'll go over some examples of when sequence can really hurt you. Some of the other things that you've got to watch out for are thread safety. And there are all kinds of aspects of thread safety. Shared resources, things called loop carry dependencies, things like that you've got to be aware of. But having said all these sort of down things, it's pretty easy, really. If you want to do something fairly simple, you want to make an improvement in some aspects of performance of either a server process or a desktop app, whatever, it's not really that hard. Just a few concepts that you got to keep in mind. You'll find exception handling is a little bit different too. It's less different than it was in previous versions of the framework, and we'll go over how some of that works too. So to jump right in exactly what we're going to cover tonight, the benefits of asynchronous programming, we'll start with that. There's some terminology that we got to cover. I apologize for that. Nobody likes that part of the presentation, I think, but we got to cover some terminology. The current methodologies in the .NET framework, again, mentioned the 4.5 framework. There's been so many different ways that you can do threading in .NET. Originally, you could create a thread. You could provision it with parameterized thread start object or something like that, fire it off, and you had a full foreground thread. You could do that. And then there's the asynchronous programming model. So you've got this kind of like you start it here, but there's a callback, and it comes back, bubbles back up over here, that kind of thing. Event-driven asynchronous programming. Probably the background worker object or class and the component model is a good example of that. You would start it, and it would immediately fire a do work event, and you had your stuff in there, and then it would give you some callbacks or some events for progress and things like that. All those things, the problem that Microsoft saw in all those things was that your code was a little bit here, a little bit there, and a little bit there. It was kind of splattered all over the place. So you would start out with, you'd start a thread, it'd run a task, and it would bubble up somewhere else in your code, maybe way off in some other region of your code. So it didn't look like synchronous code. It was always sort of disjointed. And that's what one thing they've tried to attack now in the current version of the framework, which we'll talk about, they've changed task parallelism to use something called the async and await keywords, and we'll look at those in some detail. Thread safety, exception handling, like I mentioned before, those are really important. We'll look at that. There are ways to cancel, good ways to do it and bad ways. We'll talk about cancellation. There's quite a few examples we'll go over too. Benefits, certainly there are performance benefits. I've got a couple of examples here that I cooked up that are pretty simple. I want to go through these real quick. Put my glasses on so I can see them. All right. This one, I like this one. This one's using the new async ADO stuff. And the cool thing about this is that the syntax is almost exactly like the old ADO stuff. I'll show you the syntax in a minute. So, but if I run this synchronously, there's a couple of things we'll look at here. I'll run this synchronously. What this is doing is I've got a store procedure that doesn't do anything but a delay. It just does a delay, wait 3 seconds, return a string or something, and that's all it does, 3 seconds. So synchronously, the usual programming, then it's going to take about 6 seconds, right? Each store procedure will run, then the next store procedure runs, 6 seconds, right? Running this asynchronously, by golly, it's 3 seconds. Well, okay, let's run it twice. Okay, it's about 4 seconds. And that is one thing that is a true statement, a fair statement, is that just because you throw 2 threads at something doesn't mean you're going to double your performance. It just doesn't. There's going to be some overhead involved. Usually this does run twice as fast, but you can expect that the more threads you throw at something, you may reach a point where you don't have any performance gain. You might even go the other way. So something to be aware about there. And we'll talk some more about that too. The code behind this is really simple. Thread this over here. So all we're actually doing that's different, if we look at these methods here, what we've got is the usual stuff you would just have the connection.open method and the execute reader method. And the only real difference here, I've got some console write lines to show the threads that the different things are running on. But you've got open async now, and you've got execute reader async. And those are the difference in the keywords. Now, the other things that you'll notice, you probably have heard about or are familiar with the async and await keywords. That's what really makes this work. So they've given us these new methods, so we don't just now have begin execute reader, end execute reader. We've got execute reader async, for example. There are a lot of those in the I/O world in the .NET framework. So what this does is it allows us to run asynchronously, and the other thing is that it doesn't take up, one thing is it doesn't lock the user interface. So if I run this guy here, the user interface is free. Whereas if I do it this way, using almost identical code, it's locked up tight. And we'll go over a lot of examples of the syntax that makes this work, but it looks like sequential code is the bottom line. So the other thing is that when this is running, if I run this asynchronous piece, if I go up here real quick and pause, then what I'm going to find, if I can get to my parallel tasks window, parallel stacks window, those 3 threads are the 3 threads that are always there. So right now there aren't any threads involved in the 2 outstanding operations that are hitting the database. What they've attempted to do with async and await is that if it's an I/O operation, then they wrap up the context of the thread at the point where the asynchronous I/O operation starts. They hand it off to the I/O subsystem. They put the threads involved, the background threads, back in the thread pool. And then when the I/O returns, they pick those 2 more threads up out of the subsystem or out of the thread pool, re-provision them, and then carry on from that point on. So right now, it's freed up the 2 extra threads that it was going to use to do that processing. So that's one example. Now this one, it goes into a folder on my hard drive here, and it picks out a whole bunch of pictures, and it looks to see how big the longest edge of the picture is, and it just makes it 1024 by 768. It's just a brute force sort of a way to consume some cycles on the CPU. So it goes through that synchronously, and it's going to take about 20 seconds. So we'll run through that one time. And we'll see the other extreme here when I run it asynchronously of the number of threads that are going to be consumed by this process. And the other thing is that the performance improvement is not as dramatic, not nearly as dramatic. So we'll let this time out. All right, about 21 and a half seconds. We run it synchronously, or asynchronously rather. And I'm going to go ahead and pause. And again, bring up the parallel tasks, or the parallel stacks window. I think this time we're going to see more threads, like a whole lot more threads. So how many did we end up with there? So we got 6 threads. We got one, here's the operating, basically the UI thread over here. We got 6 other threads doing other things. So this is running something called a parallel for each loop, which we'll take a look at. And it arbitrarily determines, based on your local hardware, the task at hand. It does some partitioning, and it figures out how many threads would be the most efficient on your current machine to do the processing. So it's picked out quite a few, 6. I've seen as many as 12 when I've run this before, just messing around with it. So, but it does all that for you, so you don't have to worry about that part of it, you know. And that's also something that it does. That's one of the advantages, I think, of the just-in-time compilation, is that it knows about the local machine and it can make the right decisions about compilation and threading at the time of a runtime. So there's 2 things there. One is that it let it run. One is that it used a lot more threads, and the other thing was that it didn't cut the time down but by about 20%. So those are the kinds of differences that you might see. One reason I think that the performance enhancement's not quite as dramatic is that the graphics operations in .NET are multi-threaded. So you can see, if you watch like Task Manager, you'll see a little extra activity going on even when it's run synchronously. You'll see more than one core engaged. But you run it asynchronously, and I've got essentially four cores are on the machine, 4 that show up in Task Manager, and they're all pretty busy. So it really improves the throughput, the CPU throughput. All right. Responsive user interface. If you're still in the desktop world, that's you've got to have a responsive user interface anymore. If you're going to be doing WPF or whatever, people don't like the hourglass at all anymore. They've gotten used to responsive user interfaces. The CLR makes it pretty easy to do threading, to do asynchronous coding. We'll look at some syntax examples. It's pretty straightforward, really. And of course, the most important factor, I think, for doing asynchronous programming is there's a massive cool factor. It's hard to beat. So just a little bit of background, some terminology. I promise I'll keep this fairly short. A thread, essentially, every process has got at least one thread. Some processes are going to have bunches of them. You can see there, Internet Explorer's got 38 going, Outlook's got 36 or 32 or something. So every process is going to have at least one. It's called officially a thread of execution. It's the smallest element that the operating system can schedule and run. Each one has a fair amount of overhead with it. It's got some stack space. It's got a mega stack space. The way that it works, because on the CPU side, you don't have a bunch of threads. You've got a couple of threads, right? And in a core that's not hyper-threaded, you got a thread. You know? So in the software, you've got virtual threads is what's happening. So in an operating system like Windows, it's called preemptive multitasking is what happens. So each thread potentially has a 20 millisecond time slice. And the scheduler in the operating system can give it 20 milliseconds or a tiny, tiny bit of time or no time at all, depending on the context of the thread at the time that it comes up for review by the scheduler. So that's the way that, well, there's two things there. One is when you had a single hardware thread and it looked like you had a multi-threaded application because it was responsive, that was because of time slicing. So it gave an application the ability to receive a message, like if it's a Windows form, and be able. So yeah, it's got about a mega stack space is consumed on every thread. The other thing is that some of the expense, the overhead of threading, is if you run too many threads, or if the work that you're doing on threading is very brief work, then there's overhead in switching from one thread to another. It's called a context switch. And when you do that, it consumes resources because it's got to reprovision the thread that was not running before, and it's got to put it back on the hardware thread to run. So there's a fair amount of overhead that goes along with that. And that's one of the things that keeps you from getting the doubling and tripling of performance when you add 2, 3 more threads, that type of thing. Yeah?
You said everything's going on the stack. Is nothing going on the heap?
Well, each thread is provisioned with an amount of stack space. So, but that is what's kept up with the thread. There are things certainly on the heap and on the managed heap. But what is specific to the context of a particular thread is just the stack stuff. Okay. All right. So concurrency and parallelism. Concurrency means it appears to run simultaneously, and that's what I've mentioned several times about in the old days when you just had a single hardware thread. And it looked like it was running multiple threads, but it really wasn't. So, but parallelism is when things truly run at the same time, and that's when things really get interesting. So thread safety, as I mentioned before, is one of the key elements of successful asynchronous processing. And the first thing that you got to be sure of is that you don't have any race conditions. All right? Well, what's a race condition? That's a section of code which really needs to run sequentially. It's maybe there's shared elements that are going to be accessed potentially by multiple threads, and you don't want that to happen. If they're going to change shared elements, then you can come into some pretty strange scenarios, some strange errors. You can see I've got one example here that I can run it like 10 times and it won't fail, and that 11th time it'll fail. And sometimes it'll fail 5 times in a row and it won't fail for 3 times. You know, can you imagine though if you had something subtle like that in production and it was running like once a week it failed and it just gave you the wrong answer? And you look at it like, what? This is impossible. You know, somebody's made a mistake. My code can't do this. It's not possible. But that's the kind of thing you can run into with asynchronous programming. So a race condition is a section of code. Well, a race. Let's go down a little farther. A critical section is a section of code where you don't want parallel access to occur. A race condition is a condition where in a critical section you have multiple threads accessing that section of code at the same time, and you don't want that because it has undesirable effects. So that gets into the next thing we'll talk about is the Microsoft terminology in the task parallel library. And there's 2 main divisions in the task parallel library. One is data parallelism, the other is task parallelism. Data parallelism is where you've got the same operations are going to be performed on items in a collection or array, whatever. It's like a loop. It looks like a loop. The syntax is parallel.for, so it implies it's a loop. The other one is parallel.for each. And what happens behind the scenes is that the framework does what it thinks is necessary to chunk this up. It uses a partitioning scheme called chunking to chunk up the objects in these collections. It may, in one iteration, it may pull 1 out. It may pull 3 out. It makes that decision. And that's one of the things that can guarantee you that things occur out of order. This will include the parallel for each, the parallel link or p-link. And one side effect of all of these is that they do a thread join. In other words, they lock up the hosting thread during the time that they process. So if you start a parallel 4 and expect to get a responsive user interface during the time that that's running, you won't, because it's locked up. You've got to launch it on another task or something like that if you want it to be responsive. Syntax examples. The first one is the parallel 4, and it looks a lot like a for loop, doesn't it? But it's a function. Lambda expression. You can call another method. You can have a whole bunch of code in the lambda expression. It's just a lambda expression. What happens there is that the increments are going to be from 0 to 19 is 20, the first element there, and the for call, is the inclusive start point. The second one is the exclusive endpoint, so 19 would be the highest number that would be processed. And I that's passed into the lambda expression is the counter. So as it loops through, then it's got access to that counter. And that's just a simple example where it's creating some new class, and it's calling a function on that class, and it's using that I in the constructor and that type of thing. The other one is something that you can enumerate through like a list, for example, I use here. So you've got parallel for each, and the first argument there is the list that you're going to traverse, and the second argument is the lambda expression. And there's 40 overloads for this, okay? So we're just kind of scratching the surface here. I think there's 12 overloads for the parallel 4, and there's 40 overloads for the parallel 4 each. So you can pass in cancellation tokens. There's something called a parallel loop options collection that you can pass in. There's all kinds of stuff you can do. If you can think of it, it's probably in there somewhere, if you can find it and figure out the lambda expression syntax to make it work. So those are the two cores of the parallel or the data parallelism. So these do include some default partitioning, whereas you give them a big collection, they'll chunk that collection up to some degree so that it may take 2 or 3 at a time out. It may just use 1 at a time. It makes that decision based on whatever magic is coded in the algorithms in the task parallel library. Like I said, the calling thread is blocked until the loop completes. And you can stop or you can break. And I've got an example of this in a minute. It kind of winds down, though, when you do that. You know, if you just start a thread, you can abort it, right? You can just stop that thread, and it'll just stop right in its tracks. No cleanup, no nothing. In the parallel, the task parallel library, you don't have that. You've got cooperative cancellation, and you've got the ability to do things like you can cancel processing in a loop, or you can stop it, but it just kind of like winds down. I've got an example of that here. Kind of like to go to that example, actually, instead of that. Yeah, here we go. This is the same sort of thing. If you encounter an exception in a parallel loop, which I throw one here. So what this is, all this is doing is it's going through like from 0 to 24, and what I'm saying there in about midway down is once the counter gets to number 1, which is the second one in the loop, you would think, to throw an exception right there. So at that point, what's going to happen is the pending, it's not going to spin up, it's not going to go through any more of the loop, it's going to stop the loop processing. It's going to complete any that are pending processing, though. So if you've got any that have already started, they're going to continue to run, and they'll finish running. So if you take a look over here at the screenshot, the error message the kaboom gets raised at number 1, iteration number 1, which is second from the top on thread number 9. But there's all kinds of other stuff that was still working away, and it continued to work. So you don't just stop it. You know, you can. And the stop performs, I believe, the same way. So if you stop one of these parallel loops, it actually kind of winds down. Anything that's in process, it's going to continue to process until it's complete. And I don't think there's a way to just abort a loop or a task in the task parallel library. And we'll look at cancellation on the task side here in a couple of minutes. See if I missed anything here. Yeah, this was kind of what I was saying. No new steps are started. If there's an unhandled exception, no new steps are started. The current iteration is complete. it does come back in the calling thread, so it's not like buried somewhere. Oh yeah, it's an aggregate exception. In a parallel loop, what you get is an aggregate exception. So it inherits from exception, of course, but it's got not just, it has a collection of internal exceptions or other exceptions. So you almost have to have a recursive error logger if you want to go through and get every exception, potentially. Now normally you don't. Well, I do have an example here that, see if I can find this one. This one, when it runs and it blows up, what happens is we get anywhere from 2 or 3 to maybe 10 error messages back. I'll show you what I mean here. So this guy here, if I go down to this unsafe collection, so what I'm doing here, and this is a thread safety violation. I'm taking just a generic list and I'm just pounding it with adding stuff to it simultaneously. So it's just not equipped to handle that. Just can't do it. But it'll do it for a while sometimes. I mean, it'll work for a while. It really tries. It's a very valiant effort. See if it didn't even blow up the first try. Let me up the number of. There we go. So I've got this collection of exceptions that comes back. So once this thing is corrupted, once this list object is corrupted, there's a whole bunch of exceptions that happen because these other threads, they're just continuing to go on, right? It's an unhandled exception, but anything else that's in process is going to wind down, right? So you got to keep that in mind. You want to be sure you get all the exception information that you need. And just about every time I run this, it's going to be different, and occasionally I'll get different error messages too. That's pretty consistent right now. Yep, there's a different error. So you get an aggregate exception back when something blows up in a parallel loop. All right. Now the other half of the equation here in the task parallel library is task parallelism. And that's more like you've got a case where you've got multiple operations you need to perform, and they may be in some dependent order. So let's say you've got a starting point here, and you've got this task that's going to run, and this task runs after it because it depends on the results of this task. And in parallel, you can run this task because it doesn't care, it just needs to be run. And then they join down here at the bottom somewhere. Well, that's what the task parallelism is about. So you can launch completely different operations, whereas in the data parallelism is kind of in a loop, and you were doing the same operation on each item as you iterated through the loop. So in this case, a task is essentially a thread. The task class is going to have a thread, and it basically the task class gives you tools to manipulate that thread's life. So this is the big news, I think, in the 4.5 version of the task parallel library is the async and await keywords. The idea here was to eliminate all that. You know, as I mentioned before, the older models, you would start somewhere and you'd have a callback, and it would call back somewhere else, and maybe it had to do something else, and it would call back somewhere else. And that's what Microsoft wanted to eliminate to a high degree with this async and await keyword pair. So async marks the function as awaitable, essentially, and await signals the compiler to take some special action. So what really happens is anything that follows the async keyword, under most circumstances, is going to end up in a callback. But in your code, it looks like it's sequential processing. So it's pretty slick what they've done. So it looks like you've coded just like you always do, but it actually suspends at the point of the await and then picks back up when the parallel task finishes, and it picks up at that point. And we'll take a look at that in just a second, exactly how that processing works. So here's a syntax example. You can see the await keyword, or the async keyword here, and this was the ADO.NET stuff, the new async stuff. Any of these new I/O methods, for example, that they've added, and they've added quite a few to the framework that run async with async and await. They're going to have an async suffix. So you can find those in a lot of different places, in a lot of the frameworks like file access, obviously network access like the SQL stuff, things like that.
Is that kind of like defeat the whole purpose? You use the await keyword?
Well, no, because it doesn't stop processing there. What it does is it bundles up everything. If it's truly an await at a point where it's going to be asynchronous, it bundles up information about that particular thread, saves it off on the global heap, and then it continues to process on that primary thread. So, but then when it returns from processing on the secondary thread, then it says, okay, I'm back, and it's like a callback, except it's in line. So you remember that parallel ADO example, the first one I had, where the user interface was still responsive? It followed an await. And so it looked like that, you're right, it does sound like that it would suspend right there and lock that hosting thread up, but it does just the opposite. It wraps up the context at that point. The host thread continues on. There's another task that goes on, and it comes back and makes this callback later on. So awaitable functions always return tasks, and it's kind of funny how this works. It feels okay after you do it a little bit. But if you're going to return a string from a function that you can await, it's going to be a task of string. And then what the result is the string. I'll show you some examples. It's kind of hard to describe. Also, the threading thing I mentioned before, if you've got something that's performing I/O, how if it hands off to the I/O subsystem and then puts the threads back in the thread pool. It keeps that context on the heap. And when the I/O subsystem calls back into .NET, then it picks that back out, reprovisions 2 or whatever number of threads out of the thread pool, brand new threads. And meanwhile, those threads were dumped back into the thread pool, and they were usable by other processes, or by the process for other tasks.
I have a question.
Yeah.
So in a standard data access class, where you have this common CRUD operations,
Mm-hmm.
Would you put async stuff, make an async version of like everything happening async, an ASP.NET application, for example?
You certainly could. I mean, in an ASP.NET application, when this is going to run on the server, the touted advantage is that it releases these threads. So your server is using threads out of the thread pool for each request that comes in, and ideally, what's happening then is those are now available for more requests. So it reduces the load on your server. Is the idea behind it. Now, whether or not that's true, you got to test it, though. If you got your database server on the same machine, it's like that. Maybe the overhead in dropping these threads out and I can't say provision. Well, I just said it, didn't I? The overhead involved there may be such that you don't gain anything. So you got to load test it. All right, and again, the ADO.NET example, to convert one from one type to the other, it's really straightforward. You add the async keyword and you add the awaits in front of the awaitable things that return tasks. So then the connection is going to return, I don't even remember what it returns. It just connects. I guess it just performs that operation. And then the execute reader async will return a task of data reader. So that's what you get back, but then you're able to use that as a data reader. So again, I've got some examples of that.
Is the result of generic, or is it like, how does the type one?
It's technically it's a task. So you can't await at something that doesn't return a task. And so like in this case, it's a task of type reader. But when it gets back to the await unwraps that, and then what you end up with is the data, is the result that you're looking for. I got some more examples I'll show you. So you can, yeah, it's a lot easier to show, I think, than it is to describe. Here's some pretty good example, I think, of how the data flows. Obviously, it's going to start at the. This is a complete console app, by the way. So everything but the using statements. So it goes in initially into the first part there, the do it statement, and it calls do it. Goes down into do it, and then there's an await. So at that point, it goes off into this return a string. And then, Keith, this may illustrate a little bit better. Because you see each one of these, like this is going to return a task of string, the one that it's in right now. but it comes back as just a string. So I can, up in this particular one here, I can declare a string variable and await it. It returns a task of string, but I get the string back.
You don't have to do anything to get it out.
Nope. All right, so then it goes down into this routine, and there's a delay, 2-second delay, asynchronous delay. So at that point, it says, okay, I've got to await this. It's actually off doing something. I'm just going to go back up to here. All right, so it goes back up to there, where it started from, the next line after the do it call. And then down here on another thread, this happens. After the 2 seconds times out, this is a different thread now. So it goes from there back up to here, and at that point, that thread's done. So it does the console.write line, it's off, gone. See this right here, the little squiggly green line here? You'll get a code time warning that says this is going to run sequential because you're not awaiting anything in here. You can't await the sleep because it doesn't return a task. All right? If you try to launch it in another task and await that, then it just goes off in the la-la land. I've had no luck at all doing that. I've got an example of that too. So that's what happens. Then the processing goes from here to here to here. It sleeps for 2 seconds. It goes to the return statement, actually, not all the way back up to here. Then to here, then all the way back up to there, and then to there. So then you've got the reverse of what you had before, because in the previous example you had done, and then thanks for all the fish. Now you've got thanks for all the fish, and done. It was sequential. All right. So here's an example where we've got a function. These takes a while functions, each take 2 seconds, let's say. So then the question is, the way that this is coded right now, how long would it take for the entire routine to run, roughly? Anybody want to hazard a guess on that? Anybody else have a different idea? 2, 3. It's going to be about 6. Yep. Because it's going to start that task. It's going to do an await. It's going to compile a callback essentially that after that task is done at this point, then it's going to come and run the second one. And the same thing's going to happen. Then it's going to run the third one and await that. And then at the end, then you'll get the console write lines. So that's going to take about 6. How about this one? I'm hearing 2, mostly 2, I think. Roughly 2. Roughly 2. That's right. So what happens then in this case is that the same sort of action happens, but all the tasks are running. Right? So nothing is held up at all. So don't do this, though. The reason is when you await like this, when you await sequentially like that, if task 2 completes and task 1 has an exception in it, you'll never see the exception. It just gets buried. So what you want to do is you want to do something like this. Let me say it a different way. If task 2, which is the first one being awaited, has an exception, you'll catch that one. You'll never catch any exceptions from task 1 or task 3. All right, so this is a sort of a cleaned up version of that. So I just started everything as part of the creation process, added them to a list, because these are just objects. You just add them to a list. And then down at the bottom, one of the overloads for the when all statement is to wait for a list. All right, so you wait for all of them. It waits until they're all done, and then you can you get all the information that you need about the process. All right, the new ADO pattern. Can you see that? Is it big enough to kind of? Okay. The thing I just wanted to show here was that there's not that much different to it. You know, when you get into the routine here, it's you just call this run command, and it could just as easily have been coded with the open instead of open async and execute reader instead of execute reader async. It would have looked almost exactly the same. One of the few differences, I guess, would be you've got this task.whenAll piece that's going to do a thread join. Other than that, it looks almost like the regular stuff, except it runs asynchronously. So that's an example of some of the new special sauce. And this also being an I/O process would release the threads during the runtime too. All right. Exception handling is pretty much the same as what you expect when you're doing regular sequential coding with the async and await. It bubbles up through the awaits. It looks a lot like sequential code. Here's an example. So let's see how it does. Okay, so it just calls a task. It awaits a task called some task, and it awaits some other task, and it sleeps for 3 seconds asynchronously, and then it throws an exception, and then it bubbles right back up through the stack there, and it's caught in the try-catch block. So it looks a lot like just regular sequential coding. You know, you don't have to worry about like a continuation task, things like that you had to do in the 4.0 framework, or callbacks and things like that. So it looks a lot like sequential coding. One thing I found interesting, though, is that if you launch that task in another task, then you don't get any results back. And that kind of threw me. I'm not really sure what's happening there, to tell you the truth. I thought I'd throw that out there. Yeah, I don't know if it's something similar to when you're doing those 3 awaits in a row, like I had in that one example. I said, don't do this, or exactly why, but just nothing happens. You don't catch it. It never hits the break point. All right. Another example, this is a try-catch around an await. And in this case, it's similar to that. Around the await, it traps the error. Everything works just like you'd expect. It's asynchronous. You got the all done completes first. And then the exception happens asynchronously, and it posts back to the console just like you would expect it to do. This one, it never hits the breakpoint. If I try around that, I guess it's because, I don't know. I really don't know. I was looking at this today trying to figure out why exactly this doesn't. Can anybody look at this piece of code and explain why that breakpoint never gets hit? So I'm kind of at a loss. It's certainly something to keep an eye on, though. Something about having that off in another task, I guess. All right, canceling a task. Yeah. Mm-hmm.
Aren't you catching the exception on the main thread? And
Well, it is.
Happening on the child thread?
It is. Yeah, that's exactly right. And what I would have expected, I guess, was for that to bubble back up through the awaits and then cascade up one more level, but it doesn't seem to. If I've got the try-catch around that await in that middle routine, the do-it routine, it catches it. And I guess I would have expected that if I went up one level higher, it would have bubbled up, but it doesn't seem to. Uh-huh. I tried that. I did, yeah, and it still didn't, because I just caught it there and I just threw, thinking maybe, well, that'll bubble it up, and it didn't do it. Yep.
You have to catch it the afternoon?
I don't know.
I have used not in this type of code, but in another place, a list of validation errors
Uh-huh.
that is referenced to all of the various tasks, so that when it comes back up, it has captured all of the errors.
Okay. How was that again now?
Now, you have a list of validation errors.
Oh, I see. Okay, then you just pass that back up. Yeah, okay.
You pass it as a reference argument.
On this one before we move on? All right. Okay, canceling a task. One thing you don't want to do is set your task equal to nothing or null, because you just lose control of it completely. It keeps going. It doesn't care. It has no impact at all on the processing. So in the task cancellation world, what we've got is cooperative cancellation. The task has to want to cancel. It's a very touchy-feely thing. You can't just do an abort. So what you've got is a cancellation token source, which you can get a cancellation token from, and you can use that cancellation token over and over again. So you can have all kinds of different tasks that are running that use the same cancellation token. And on that cancellation token source, if you call the cancel method, they all cancel. All right, they all if they're willing to cancel. They've got to watch for that, so they can see this cancellation request, and They can throw up a specific type of error that will change the status of the task, at least briefly. You've got to be a little careful with that too. So it's up to you how you cancel it. The nice thing is that it gives you the chance to clean up, so that if you say cancel and your code polls for it, typically is how you catch it. You can use a delegate too. But if you poll for it, then you got the chance to clean up a little bit before you exit the task, for example. So it's kind of a nice model. Works out pretty well, and you can use it in tasks, and you can use it in the data parallelism. There is an overload out there somewhere in Parallel 4 and Parallel 4 each will allow you to pass in a cancellation token. So, thread safety. We'll talk a little bit about thread safety. These are some things that are thread safe. Each task gets its own instance of a working object. So it's got its nice encapsulated piece, and it calls a method on it or something, and it just lets it go off and do whatever it does. Unless there's static variables, right? So if something changes a static variable, could be anything. Change the static variable. Well, if you need that static variable, then maybe you don't want it to be changed, right? That could cause you a problem, make it not thread safe. Or you pass in a reference variable. Some other thread somewhere else in the application decides it wants to make a change to that, and it changes everywhere that's been used or referenced. Third-party stuff, it's kind of a black box. You don't know what you got. So you've got to watch third-party tools. Are they thread safe? Maybe they'll tell you they're thread safe. Maybe it's in the literature. Maybe not. Maybe it's just not.
Are these objects that we're talking about here structs?
No, not necessarily. Could be.
Because if they're getting their own instance, and you're not pointing to a particular location in memory.
Right.
Because as soon as you point to if you have multiple instances and they're all referencing the same object.
If you're just running multiple threads through an instance of an object, and there's just calling routines in that instance of the object, then there shouldn't be any problem unless you've done something else that, like I say, you pass in a reference variable to a function call or something like that. As long as it's fairly well encapsulated, you should be in pretty good shape. But that's the kind of stuff you got to be aware of, though. I mean, you got to look at everything. You know, if you're going to get into a complicated asynchronous scenario, then you've got to look at it. Otherwise, you're going to have that once-a-week error that bubbles up, and you get the phone call in the middle of the night. You know, it's pretty touchy stuff in that regard. Anything else on this particular slide?
If you want to make the object thread safe, is there something called an critical section?
That's you can you can certainly lock a critical section. I think I got some slides on that.
Are there some new keywords?
No, there's no. It's still lock in C#, for example, or monitor if you want to monitor. Use monitor instead.
There are thread safe objects too, like concurrent bag.
Going to get to that. Yeah. This is just the first slide. So you're right. There are. There are some things and they don't block necessarily either. So yeah, we'll get to that in just a minute. But yeah, critical sections, you can block them, lock them. The problem is, and one thing you got to be real cognizant of, is if that critical section is getting hit all the time, are you gaining anything by making it asynchronous? You know, that type of thing. But yes, you can. Multiple threads share an object, but there's no changes to static or shared variables. You're probably safe, unless something else externally changes your shared or static variables. Shared routines, static routines are not necessarily, you see in all the Microsoft documentation, static routines are thread safe for this particular class. Well, that's because they've coded them that way, right? They're not just inherently thread safe. Here's an example. List of T is not thread safe. This is the explosion I had in the one app where we got all the error messages in the message boxes. This is the kind of thing that caused that to happen. It's just not thread safe. So you got multiple things trying to add things to it, and boy, if I was trying to take things out too, like producer consumer stuff, oh, it would have blown up quicker even. Not thread safe. There are, as you mentioned, there are thread safe collections, and there's several of them. There's a queue, there's a stack, there's a concurrent bag, there's a concurrent, what else? I've got a list. Concurrent dictionary, several of them, and they do a pretty good job. That's how in that same example I do a threadsafe example doing the same thing. I use a concurrent bag and a concurrent dictionary, both. They do things differently, and you got to read the documentation. Some of them have specific purposes. Some of them aren't real fast. Supposedly in the 4.5 framework they've sped some of these things up a little bit, but you got to read the documentation and pick the one that's right for your application. Multiple, yeah, as I said, that's kind of redundant. Multiple threads share an object and call routines that may alter static variables, for example. This is kind of interesting. If you got a line that's like just an increment, like a plus plus, that's not thread safe. No way. If it's incrementing a shared variable, it is not thread safe. And we'll look at some pseudocode down at the CPU level in just a minute on that. Loop carry dependencies. This is kind of a subtle one. If you've got this is a regular for loop that would probably not be a good candidate for parallelization. Parallelism. What happens here is that as it iterates through this loop, then it's referring to a value in a previous iteration. So data I equals data I plus data I minus 1. Data I minus 1 might not have been hit yet. All right, that's a loop body dependency. If it hasn't been hit yet, run yet, you're going to get the wrong answer. And then you get that phone call. File access. They've added some things that I think are thread safe calls in the file system I/O stuff. I haven't looked at it yet. I just noticed some verbiage about some changes. But simultaneous file access, if you're writing in a way that will even allow that, is going to be probably kind of a mess. Now here's I picked this up online somewhere. I thought it was a really good example. Got a shared variable I. So you've got one thread, it reads that value, it's initialized to 0. You got a thread that reads out of memory, puts it in register 1 because it's going to operate on it. You got another thread, same time, gets that value, puts it in register 2, it's going to operate on it. You're already messed up because both those threads think that the value is 0, right? So it's not going to increment right. So the first one adds 1 to it, second one adds 1 to it, they both put it back in memory, it's still 1, should be 2. Classic example of a race condition. Collections we were talking about. I think this is the complete list that we've got, as I said before, though. So if you're going to loop through something and add things to a list as part of your asynchronous processing, and multiple things are going to do it at the same time, some things may be adding, some things may be taking things away. You want to probably consider using one of these guys. Because they'll make it thread safe. And they also don't necessarily block to do this. They've got other mechanisms of doing things that I don't understand, but that will make these collections thread safe to use. So canceling a task, as we said, cooperative cancellation. This is a little redundant. Yeah, that's redundant. Never mind. Yep. Polling, yeah, I mentioned polling. You can register a delegate. Okay. Make sure there's a payback. To summarize, make sure there's a payback. You don't want to go through this if there's not. I mean, it's not, like I say, it's not that hard, but it can take longer to code. But if the payback is there, why not? I mean, the hardware will support it today. You've got a great language to use in C# or VB.NET. Why not? Take advantage of it. Thread safety, of course, is key, as I keep saying over and over again. I've been bitten by it before. Can't rely on sequence. Timing is everything. I had just one example in the desktop world where we launched off something. I think it was a request to find all the servers in the general area on the network, SQL servers, and had a cancel functionality. Right? It's async, so hit the cancel button. Dialog goes away. 5 to 10 seconds later, you get an error message. It's like, can't create handle. What the heck? Well, it returned. I mean, just because you killed that form, it didn't mean that thread was going to stop running, right? So that process was still going out there. It called back in, and it says, okay, I'm going to display a message that this, and there was nothing there to display it on. The handle of the form or the control that it wanted to use was no longer there. So timing is everything. Understand the exception handling. And if a process is closed, this is something I haven't mentioned elsewhere in the presentation. If you've got operations running and somebody's going to shut down your application, whatever type it might be, you might want to keep track of the tasks that you've got running that are important to shut down gracefully. Because if you do anything with the TPL, it's going to be a background thread, and it will not keep the application from shutting down like a foreground thread would. So that's it.